Okay, so I wanted to go over worksheet 1105 on basic instructions and addresses, and actually on the back side we also have timers that we need to understand as well. So on this worksheet, what I am giving you is 3 tables, and we are going to use our imagination and say that these are live running tables. So it's live data from the PLC. And then I have some instructions down here that we want to see what the result would be if those addresses were compared against these tables up here. And of course, I don't have the green highlighting here on the page. That would be a dead giveaway. So this would just be looking at an instruction compared against the address to determine if it has logical continuity or not. So what we're going to do is look at this first instruction here, and this is a test instruction. It's going to test this address to see if it is a specific value. That instruction is called examine if closed. So the instruction looks like a normally open set of contacts because the only thing a normally open set of contacts can do when it goes to its active state is close. Now, the address that I have there is not an input or an output address. It's an internal address. So there physically aren't any contacts associated with that address. So this is a good example of how this instruction, I give it a nickname of test for 1. So it's testing for the value to be 1. And in that particular address, if it is a 1, we are going to pass the test, and by PLC terminology, we will have logical continuity for that instruction. So let's go ahead and put it to the test here on our worksheet. We have B3, so we know it's a binary address. So we're going to have to come up here to the binary table, okay? And in that binary table, all of the registers are B3, and we have to go to the next value here. This next number is the word. So the word number 4 is all of these 16 values that are lined up next to each other. Okay, so that's the binary B3. You can see B3 right there. And then the word 4, which is that 4 number right there. And to get down to the bit level, which is what this instruction is it's a bit, what they call it, a bitwise instruction. We have to define the address down to the bit. So it's the 15th bit in that word. So where do we find the bit numerals? It's here. They're the columns in this particular table. And this is the 15th bit right here. Okay. So that is a 1 in that particular location. And my nickname for this instruction is a test for 1. If you think about if this was an input address and these were contacts that were coming in from the field, if they were closed, we would be sending control voltage in, which we would store in the table as a 1. You can think about it that way. So that's why we used an examine if closed here. So in this case, we passed the test. This instruction has logical continuity, and the answer to that question is true. Let's test the next one. We have the polar opposite instruction. This is an examine if open. And an examine if open, its nickname is test for 0. So we're going to go to its associated address and look at that table to see if that value is a 0. We are now going to look at a different table. It's going to be the output table. And because we're talking about a physical address, we have another number associated here. This is going to be our slot number. And in this class, we're always going to be dealing with slot 0 because all of our input and output channels are on our PLC. We could add more by adding cards. And when we add cards, we add them into slots, and they just go up numerically. So the next card we add would be slot 1, slot 2. But everything that we're going to be dealing with is slot 0. This number right here is the word number. A slot could have more than 16 channels on it, and because of that reason, we're going to need more than one word. And so we have a word value there. So let's go to our output table. So right here you see the output table, okay? And we said that it was output 0.3, slot 0, word 3. So that's going to be all 16 bits along here, okay? And then we have to know which one. This is a bitwise operator as well, meaning we have to specify the address down to the bit, and in this case it's going to be the 12th bit. And so that 12th bit we can find right here in this column. So we'll mark that with a 0. Okay. Now remember what my nickname was for this instruction, test for 0. Well, when we went to that particular address, we found a 0. So since we tested for and found a 0, we would have logical continuity as a result of this test instruction. And so the answer to number 2 is true. We do have logical continuity. Let's look at the next instruction. So now we're looking at an input channel, and we're back to our examine if closed instruction, or a test for 1. And this address, we go up to a different table. We have to go to our input table here. So we're dealing right here, okay? Input table, and our word is slot 0, word 2. So we're going to come up here to slot 0, word 2, and it's going to be all of these values in the word. Is that entire word? Okay, so that's just that part of the address, and this again is a bitwise instruction, so we have to go down to the bit level, and we have to go to bit 7, and all the bits are in columns on these tables. So here is my 7th column, bit 7 column for all the words, and in our case we're just looking at that bit right there. Okay, now remember my nickname for an examine if closed is test for 1. Well, we went to that address and we found a 0. Okay, so it did not pass the test. If it does not pass the test, we do not have logical continuity, and therefore the answer to this one is false. Okay, so now we're in a new instruction here. We have our output instruction, and this one's called output energize. So it's going to take whatever rung value is tied to it, and it's going to write that value to the address that's associated with that. It's called a set instruction. It's going to set that value to that particular location. So we are going to reverse engineer to answer this question. We're going to look at that address and see what value it is. And if it's being set to a specific value, that'll tell us whether we have rung continuity or not. So we're going to go back to our B3 table, and in this case it's B35. So that would be right here. That would be this entire word, okay? And then down at the bit level, we want to look at bit 4, okay? So we're going to come to this column here, and this is bit 4, which is currently having a 0 written into it. So if it has a 0 written into it, that means whatever is coming in on this rung is going to be false. Something in that rung, or multiple items in that rung, might have de-energized, in logical terms, that rung, and then we had to start writing a 0 to that output. So the question, or the statement, says this line has rung continuity. That is false. It does not have rung continuity, and that's why we're writing a 0 there. So the answer here would be false. Okay. Let's come down and let's look at some timing functions. On the left column here, this is the time on delay, and on the right column here is the time off delay. We're going to go through the time on delays first, and we'll look and see how they behave, and then we'll examine the time off delays. Okay, so both sets of these timers are what we call non-retentive timers. That means they will not retain their time, and so it's based on what is happening on the rung as to whether it is going to, the timer is going to reset, the timer is going to be timing, or the timer will be complete. Okay, those are our three states. The timer cannot be in any other state besides reset, timing, or complete. So let's first start with our time on delay. And we can examine our preset and our accumulated value and be able to make a determination about the three output bits. Okay, so first off, our first output bit is our enable bit. Our enable bit is going to mimic whatever is happening on the rung coming in. So whatever I have coming in here is what is going to be set on the enable bit. So now we need to determine, based on these values, what must be happening here. Well, the definition of reset is, or when a timer gets reset, is when we lose rung continuity. So since we are reset here, this is a value of 0. Now, all these statements that I'm making are for a time on delay. Okay, don't get them confused with time off delay. So a reset for a time on delay is when the rung goes false. Okay, so because this is at 0, I know that my rung must be false, because if my rung is false for a time on delay, that means that I've reset my timer, which I set it to 0. So if I've reset my timer and my rung coming in is false, that means my enable bit would have to be a 0. Okay. If I've reset my timer, I am not physically in the act of timing. So my timer timing bit would be set to 0. Okay. And my definition of complete on a time on delay is when my preset and my accumulated value equal each other. I'm being very careful to use the word complete and not the word done, okay? Because done means something different between time on delay and time off delay. But if I use a generic term like complete, complete for a time on delay and complete for a time off delay are defined the same. And complete is when your presets and your accumulated value equal each other, okay? So if they equal each other, the timer is complete. If the timer is complete for a time on delay timer, that means that my done bit would be set. But in this case, my timer is not complete, okay, because they don't equal each other. If it is not complete for a time on delay, that means my done bit will be 0. Okay. All right, let's go to this next state, and let's kind of determine where we're at here. Okay, so we are not in a reset mode. Remember, reset was we had a 0 here. We are something higher than a 0. The only way that's ever going to happen is if we have a true coming in here on our rung. Because remember, it's going to time on the on transition from false to true coming in on the rung. So that means that my rung coming in here is true. And if my rung is true, that means my enable bit would have to be a 1. Because the enable bit is going to mimic whatever is happening on the rung. Okay. Because I am not complete, I am still in the act of timing, my timer timing bit will be set to a 1. Okay. I'm physically in the act of timing, so my timer is timing, so my timer timing bit will be set to 1. And my definition of complete is when my preset and accumulated values equal each other. Well, since they do not equal each other, I am not complete. And if I'm not complete for a time on delay timer, I'm not done. So therefore, my done bit will be set to 0. Okay? Final state here. Final state is I have a timer that is complete. Complete, the definition of complete is the preset and the accumulated value both equal each other. The only way that it's going to stay in this state is if my rung coming in is still true. Because if my rung was false, I would reset the timer. So the rung has to be true. If the rung is true, that means my enable bit would still be a 1. I am not physically in the act of timing anymore because I am complete. The timer has finished its function because it has reached its preset value. Now this timer, this rung, could have been on for longer than 8 seconds. It could have been on for 2 hours. But our timer, once it reaches the preset value, it just stops timing. Well, when it stops timing, my timer is no longer timing. My timer timing bit gets set to a 0. Okay. Now, our definition of complete is when preset and accumulated equals each other. And for a time on delay, complete equals done. So in this case, my done bit will be set to a 1. Okay. So that is all of the states that a time on delay can be in. And those exact same states are all the states that a time off delay can be in. So we're going to examine the time off delay now. Okay, so looking at these two values, I know that the timer is in a reset mode. Okay, the only way that this is going to be reset for a time off delay is if the rung coming in here, I lost my marker, is if this is true. Okay, remember we're timing for an off or a false. And because this is true, whenever this goes true, it's going to reset my timer. And I can tell by the accumulated value that this has been reset. So my rung coming in here must be true. If my rung coming in here is true, that means my enable bit will be a 1. Okay. Because I am in a reset state, that means that my timer timing bit will be 0. I'm not physically in the act of timing. Okay. Now, our definition of complete is when our preset equals our accumulated value, and that definition holds for both the time on and the time off. But the definition of done is going to be, for a time off delay, is going to be if I am not complete, then I am done. So done is going to be the opposite of complete. It's a little hard for students to wrap their head around, but when we get, after we look at these three states, it'll make a little bit more sense why Alan Bradley did it this way. Okay, so we are not complete. Therefore, if we're not complete, that means we are done. Okay, and when we get to the final state, it'll make sense, a little more sense, I believe. Okay, so now here we are physically in the act of timing. I can tell because we're higher than 0, but we have not completed yet. We haven't completed because the timer has not reached its preset value. The only way that we could be timing is if the rung coming in here was false. Okay? Because this is an off delay timer. We're timing when the rung goes false or goes off. So that means that the rung is false, therefore we started timing. So our enable bit would have to be 0. Because the enable bit and the rung are going to, it's just going to mimic whatever the rung is doing. Okay? We are physically in the act of timing. So the timer timing bit is going to be a 1 because we're not complete yet. We haven't reached the 8 seconds. We're physically still in the act of timing, so the timer timing bit will be set to 1. And we are not complete. So since we are not complete, remember, for a time off delay, the done bit is the opposite of the complete definition. So we are not complete, so therefore we are done. Okay? And that is all of the values for that particular state. We have one more state, and then we'll examine these a little bit closer here at the end. Okay? So now, looking at these two values, we know that we are complete. So if we are complete, that means that we must have still a rung that is false. Because if it would have ever gone true, we would have reset ourselves, and this would have gone to 0. So we still have a rung value that is false. Again, this rung could be false for an hour, but all we care about is the first 8 seconds of it being false. Okay? So, and as long as it remains false, we're not going to reset this timer. So the rung coming in would have to be false. If the rung coming in is false, that means our enable bit here would have to be a 0. Okay, because the enable bit is just going to mimic whatever is happening on the rung. Okay, we're physically no longer in the act of timing because we are complete. And since we are complete, we're no longer timing, so our timer timing bit will be a 0. And we are complete because our definition of complete is when preset and accumulated equal one another. But remember, our done bit is the opposite of complete. Since we are complete, that means our done bit will be set to 0. Okay? So here's where I think it would help the student, the explanation. It's when we get down here. We had a transition right here from a true to a false. But we wanted to delay that. We want to off delay. That's why we call this a timer off delay. We wanted to delay that off transition from true to false for 8 seconds. So if you notice, we went from true to false, but our done bit still stayed at a 1. And it wasn't until after 8 seconds that our done bit went to a 0. That is the use of this particular timing function. It's to delay the off action instead of for the timer on delay. If you notice, when we went from false to true, we delayed the on action from the off to true, the false to true transition by 8 seconds. Here we're delaying the off transition from true to false. We're delaying that off through the done bit. They're both done through the done bit. They're both expressed through the done bit is a better way to say it. Okay, so that is the difference between the time on delay and the time off delay. Let's examine here, looking across. This state here is called reset. Okay? This state right here is what we call timing. And this state right here is what we call complete. And if you notice, complete is a much more accurate way, because I can't say done, because in done, this one is a 1 and that one's a 0. So it gets very confusing to the student. So those are our 3 states for a timer. It's either in reset, it's either in timing, or it's in complete. Okay? And those are the 3 states for non-retentive timers. Now, if we look across here at the states, the enable bit is polar opposite across for all three states. See that? And that makes sense. This one's for on delay and this one's for off delay. Okay. If you look here, the timer timing bit for both types of timers is the same. So that didn't change. The active timing is still going to be the same off delay or on delay. Okay. And then the done bits are polar opposites of one another. So here it's 0, there it's 1, here it's a 0, there it's 1, and here it's a 1, and there it's a 0. So you can kind of see the behavior and how the different timers relate to one another. I hope that helps, and we'll see you in the next video.